Texan Global School. Logarithms. In this class, we will analyze the definition of logarithm and its properties. We will start by recalling the definition of logarithm seen in the previous class. The logarithm base b of x is the exponent y to which the base b must be raised to obtain the number x. We can see that b is the base, x is the argument, and y is the logarithm represented as the exponent of the base. To maintain a functional relationship, the x and y were exchanged. In this way, we represent x as the independent variable and y as the dependent variable. Let's see an example. Let us find the value of the logarithm base 2 of 8. To find the value, we will apply the definition of logarithm, obtaining in this way that the logarithm base 2 of 8 is equal to y if and only if the base 2 to the power of y is equal to 8. Then we must look for the exponent such that raising the base 2 to y results 8. Hence, 2 cubed is 8. Therefore, the logarithm base 2 of 8 is equal to 3. This result is interpreted by graphing the logarithm function base 2 of x. In this way, we can see the relationship between the argument 8, represented as a value of the abscissa x, and the value obtained y as the ordinate. In this other example, we will find the value of the logarithm base 4 of 16. To obtain the value, we will apply the definition of logarithm. The log base 4 of 16 is equal to y if and only if base 4 raised to power of y equals to 16. So we must find the exponent such that raising base 4 to y results 16. We can see then that 4 squared is 16. Therefore, the logarithm base 4 of 16 is equal to 2. Let's look at another example. Let's find the value of the logarithm base 3 of 5. Applying the definition of logarithm, we have that the logarithm base 3 of 5 equals y if and only if the base 3 raised to the power of y equals 5. In this case, there is no integer exponent such that raising the base 3 to that exponent results 5. We will then perform iterations to find approximations of this number. Hence, start with integer exponents that are close to this value. 3 to the first power is 3. Then, 3 squared is 9. This means that the value of the exponent is between 1 and 2. So, propose values of exponents from 1.1 to 1.5. We can see that when raising 3 to the power of 1.4 results 4.655. Raising 3 to the power of 1.5 results 5.196. Meaning that we are approaching the value of the exponent that raising 3 results 5. Proposing more values, we can see that a comparable value is raising 3 to the power of 1.47, resulting in 5.027. In this case, we will leave the iterations up to these 2 decimal places. However, the decimals can be increased to obtain a more exact value. Calculation can also be done with tables or engineering calculators. We conclude that 3 to the power of 1.47 is approximately equal to 5. Therefore, the logarithm base 3 of 5 is equal to 1.47. On the other hand, it is important to analyze the properties of logarithms. The first property says that logarithms of negative numbers do not exist in the real number system. Such logarithms are complex numbers. We can see in the example that the logarithm base 2 of negative 5 does not exist, since there is no positive real number that, when raised by a power, results a negative real number. The second property indicates that the logarithm of 0 is not defined. Since an exponent is not defined when raising a base, that will result in 0. Another property says that the logarithm base b of 1 is equal to 0, since b to the 0 power is 1. This other property indicates that the logarithm with the same base and the same argument is equal to 1. We can see that the definition of logarithm proves all these properties. Now the logarithm base b and argument b to the n is the same with n. It is important to remember that the base 10 logarithm is represented without a base, as shown on the blackboard, and the logarithm base e is represented as a natural logarithm. This next property indicates that the logarithm of a power is equivalent to multiplying the exponent by the logarithm of the base of the power. Remember that if the exponent is a radical, then the factor will be a rational number. Let's see an example. We will find the value of the logarithm base 2 of 8, obtained earlier, to show that the properties of logarithms can be applied. We can represent it as logarithm base 2 of 2 cubed. Applying the power property of logarithms, we have 3 times the base 2 log of 2. Since the base 2 log of 2 equals 1, Multiplying the missing products gives us that the base 2 log of 8 equals 3. We can see that it is exactly the same value obtained using the definition. This other property indicates that the logarithm of a product is the sum of the logarithms of its factors. We can use the properties in any sense. This example shows that the property is valid. We will get the value of the log base 4 of 16. Let's express this logarithm as log base 4 of 4 times 4. Then, using the product property of logarithms, we separate into log base 4 of 4 plus log base 4 of 4. And by properties of logarithms, each logarithm equals 1. Therefore, the logarithm base 4 of 16 is equal to 2. Exactly the same value was obtained using the definition of logarithms. This other property indicates that the logarithm of a quotient is the difference of the logarithms of the dividend and the divisor. This same example of log base 4 of 16 can be represented as log base 4 of 64 over 4. Then, using the quotient property of logarithms, we have split into log base 4 of 64 minus log base 4 of 4. Then, apply the logarithm property base b of b equals 1. And applying the definition of logarithm, we obtain that the logarithm base 4 of 64 equals 3. Simplifying results 2. Therefore, the logarithm base 4 of 16 equals 2. Exactly the same value was obtained. We can also make a change to any base. Simply, the logarithm base of x can be equal to the quotient of the logarithms of the desired base b with the arguments x and a respectively. Or simply, the base with the argument is inverted and represented as a reciprocal. In this example, we will change the same logarithm base 4 of 16 to base 3. Applying the formula, the change of base remains as log base 3 of 16 over log base 3 of 4. To verify that the base change is valid, we calculate each logarithm separately with iterations, and then perform the quotient. We can see that it is the same, resulting 2. In this next example, we will simplify the following expression with logarithms. We can see that the logarithms have the same base and their arguments now have variables. So let's use the properties to simplify. In the first term, we have a factor times a logarithm, so we'll use the power property by moving that factor as an exponent. Since the third term is divided by 2, it can be represented as 1/2 times the log base 3 of x. Using the same property results in log base 3 of x to the power of 1/2. Now, since all the terms have the same base, we can apply the product and quotient properties. We first use the property of the product since we have 2 logarithms with the same base added. Then they are simplified in logarithm base 3 of x to the 4th times x. By laws of exponents, we have logarithm base 3 of x to the 5th. Now, since we have 2 logarithms with the same base subtracting, it is simplified with the quotient of the arguments. Hence, we have the log base 3 of x to the 5th over x to the power of 1/2. Using the laws of exponents, it simplifies as the logarithm base 3 of x to the power of 9/2. And with radicals results log base 3 of the square root of x to the 9th. In this last example, all the logarithms have the same base, simplifying without needing a change of base. Using the power property, we have log base 9 of x minus 1 squared. Now, applying the quotient property, we have the logarithm base 9 of x minus 1 squared over x squared plus x minus 2. We can factor the denominator as a binomial of the form x squared plus b x plus c. 2 numbers that multiplied results -2 and added plus 1. So its factors are x minus 1 times x plus 2. Then, cancel identical factors and simplify the logarithm. Finally, let us apply the property of logarithms of the product having log base 9 of x minus 1 times x plus 2 over x plus 2. Simplifying identical factors results the simplified expression of log base 9 of x minus 1. Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com